on how FN FAL works, invented by Dieudonne Saive in 1953. Documentary engineering story, 6 parts. In a workshop in Herstal, Belgium, during the spring of 1953, Dieudonne Saive stood before a prototype mounted on a test rig. The air in the room was thick with the scent of maintenance oil and carbon residue. Scattered across steel tables were spent brass casings. One wall was covered in engineering blueprints, detailed cross-sections of gas systems, bolt assemblies, and recoil springs measured in millimeters. The equipment before him was longer than most contemporary designs, heavier than the compact options American forces favored, and constructed on a principle Saive believed would outlast any political deal: adaptability through mechanical honesty. The device had a designation but no formal name yet. FN engineers identified it by project codes. It utilized the 7.6 U2 51mm NATO cartridge, a round selected not for ballistic superiority, but for political unity. Saive moved his hand along the gas tube situated above the barrel. Near the front sight, a small collar with detents caught his eye. He clicked it one position over. The internal mechanism responded with a soft sound. This collar, this straightforward rotating interface, was the solution to a question most designers never considered. What happens when tactical doctrine shifts, but the equipment remains in service? NATO officials pushed for standardization, while member nations guarded their sovereignty. American ordnance boards preferred their internal designs, and European manufacturers needed export deals to keep their doors open. Saive realized that no single tool could meet every tactical requirement, but a design that could be reconfigured might satisfy the majority. The hardware before him wasn't built for one specific army, but for various forces that often disagreed. This meant it had to operate in Arctic freezes and desert heat, using surplus supplies or precision loads, whether after thousands of cycles or minimal upkeep. It had to tolerate inconsistency. The contradiction was built into the request itself. Organizations wanted a universal standard alongside local control. They demanded reliability, but wouldn't standardize the quality of the supplies. They wanted a tool that worked everywhere, despite training soldiers differently in every nation. Saive knew that trying to please everyone would please no one unless the hardware itself could adapt. He adjusted the gas collar once more. Each setting altered the volume of propellant gas entering the operating system. More gas provided more force to drive the action. Less gas allowed for smoother operation. The mechanism could handle almost anything as long as the user knew how to tune it. This wasn't a compromise, it was a philosophy. Rather than demanding the world conform to the tool would conform to the world. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far. And stay with us for the next chapter. Dieudonne Saive was 59 years old in 1953. He had spent the bulk of his adult life designing equipment in the shadow of a legend. During the 1920s, he worked alongside John Moses Browning at FN Herstal, absorbing principles that would define his career. Browning passed away in 1926 in Saive's office while perfecting what became the high-power pistol. Saive finished that design. He learned then that the most effective tools weren't always the most innovative. They were the ones that allowed for the most human error. Born in Herstal in 1894, he grew up in a city where craftsmanship was a deep-rooted tradition rather than just an industry. His father was a worker in the FN plant. Saive began there as an apprentice, moved into the drafting office, and was leading development teams by his 30s. He lived through 2 major global conflicts without leaving Belgium. He observed how forces succeeded or failed based on logistics rather than just bravery. He understood that equipment failed not because of design errors, but because it couldn't handle variations in supplies, maintenance, training, or climate. By 1950, the Cold War had turned procurement into a geopolitical stage. NATO was taking shape. and member nations required a standard rifle. The United States pushed for the T-44, the precursor to the M14. Britain favored the EM2 bullpup. Belgium, a small nation with a significant manufacturing sector, needed to stay relevant. The survival of FN depended on winning international contracts. Saive was tasked with creating a design that could be adopted across different continents by countries that would never agree on training standards or maintenance schedules. The pressure wasn't just creative, it was vital for survival. If FN failed to secure NATO adoption, the Herstal factory, the livelihood for thousands, would lose its main export market. Saive was designing an economic lifeline for his community. He knew the equipment had to perform in conditions he couldn't foresee, for users he would never meet under doctrines not yet established. He went back to basic principles. What did every force need? Reliability. What did reliability require? A tolerance for variation. What enabled that tolerance? Mechanical adjustability. The gas regulator wasn't a specific request from military planners. It was Saive's answer to a problem they hadn't identified yet. You cannot standardize the users, the supplies, or the environments, so you standardize the ability to adjust. In early 1953, the prototype was ready. The gas system used a short-stroke piston, driven by gas but not permanently attached to the bolt carrier. The bolt secured via a tilting mechanism rather than rotating lugs. The gas collar permitted field adjustments without specialized tools. Saive submitted his work to NATO evaluators. He knew the design was technically sound, but he also knew technical quality rarely dictated political results. American influence was dominant, and Belgium was a minor player. The design would have to prove its worth not just in a lab, but in every climate and context imaginable. It had to survive 100 different tests. The FN FAL operates using a short-stroke gas piston system combined with a tilting bolt mechanism. When a round is fired, expanding gases propel the projectile down the barrel. A small port in the barrel wall redirects some of that gas into a cylinder located above. Inside, a piston is forced backward, but only for about 1 centimeter. This piston hits the bolt carrier, transferring its energy, and then stops. Driven by that momentum, the carrier continues moving back, taking the bolt with it. As the bolt travels rearward, a camming surface on the carrier forces the bolt to tilt downward, unseating it from the barrel extension. The used casing is pulled out and discarded through an opening on the right. A return spring, which was compressed during this movement, then pushes the carrier forward. This action picks up a new round from the magazine and seats it in the chamber. The bolt tilts back into its locked position. This cycle continues as long as there is a supply of rounds or until mechanical wear occurs. This specific cycle wasn't unique, as gas-operated tilting systems had been seen before. What set the FAL apart was the integrated regulator. A rotating collar near the gas port could be manually adjusted to several settings, usually numbered 1 through 8. Each setting dictated how much gas reached the piston. Increasing the gas provided more force for the action, ensuring it worked in freezing cold or with low power supplies. Reducing the gas lowered the physical stress on the device, lengthening its lifespan in ideal conditions. This flexibility allowed the equipment to function consistently, whether in the Arctic, the desert, or when using various types of surplus or precision supplies. It could keep working after thousands of cycles without a cleaning, or even after being submerged in water. The regulator was the physical manifestation of tolerance. Instead of requiring a perfect environment, the device adjusted to an imperfect one. At first, NATO evaluators didn't grasp the importance. During the 1953 trials, American officers questioned the necessity of field adjustments. Their philosophy relied on high-quality supplies and strict maintenance schedules. Why build a tool for inconsistency? British evaluators preferred compact layouts. while French observers wanted the ability to launch projectiles. Every nation arrived with different assumptions about how such a tool should work. Saive's design was tested against the American T-44, the British EM-2 and others. NATO searched for one answer, but the requirements kept shifting. Some tests focused on long-range accuracy, others on endurance under heavy use. Some prioritized ease of manufacture, others the interchangeability of parts. The FAL wasn't the absolute best in any single category, but it was highly effective in all of them. The gas regulator allowed it to be tuned between different tests, meeting new requirements without a full redesign. The pushback didn't come from mechanical failure, but from institutional habit. American officials saw no reason to pick a Belgian design when they had domestic production ready. British engineers stood by their own work. Smaller nations lacked the political clout to move the needle. Saive understood that winning required more than engineering skill. It required proving that adaptability was a strategic necessity. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. In the fall of 1953, FN dispatched prototype units to testing locations throughout Europe. One group went to Norway, where temperatures were constantly below freezing. Another was sent to North Africa, where fine sand got into every moving part. A third stayed at the Herstal grounds for endurance testing to measure parts wear and lifespan. Each setting highlighted weaknesses that laboratory benches hadn't shown. The trials in Norway revealed an issue with the return spring. The extreme cold caused the spring steel to contract, which lowered the tension. The bolt carrier moved too slowly when closing, occasionally failing to seat the round properly. When Saive got the report in December, he didn't change the spring. Instead, he told the testers to turn the gas regulator to a higher setting. This increased the gas flow, making up for the weaker spring force. The device worked perfectly. The regulator had solved a problem it wasn't even specifically designed for. In North Africa, the sand created a different challenge. Fine grit entered the gas cylinder and began wearing down the piston and carrier. After several thousand cycles, the wear started to impact reliability. Saive studied the metallurgical data and ordered a harder chrome plating for the internal gas components. This increased the cost, but drastically improved the lifespan in harsh environments. While production engineers worried the plating would complicate manufacturing, Saive argued that equipment failing in the field would ruin their reputation. The change was made. Back in Herstal, they tested the limits of the barrel. The 7.62 51 milliliter cartridge created high pressures and significant wear. After 10,000 cycles, engineers checked for erosion and tolerance changes. The area near the chamber had expanded slightly. Saive was ready for this. The barrel was designed to be swapped in the field with basic tools, no heavy machinery needed. The barrel extension, which held the locking surfaces for the bolt, was part of the barrel unit. When a barrel was spent, the whole piece was replaced, allowing users to maintain their equipment without specialized workshops. Every adjustment was logged and tested again. NATO evaluators were skeptical, viewing these constant tweaks as a sign of an unfinished design. Saive saw it the other way. The equipment was responsive. Each test wasn't revealing a flaw, but a condition that needed an adaptive response. The gas regulator, the chrome surfaces, and the modular barrel weren't just quick fixes. They were the core of a philosophy where systems accommodate reality rather than demanding perfection. By early 1954, the updated prototypes were performing well in every environment. NATO still hadn't reached a final verdict, and political talks continued. However, FN had demonstrated something more important than being the best. The FAL could be built under license by different nations, tailored to local factories, and set up for different tactical needs while remaining compatible. It wasn't just a piece of equipment, it was a platform. The turning point didn't happen during an official trial, but during an event that was never formally recorded. In the spring of 1954, a shipment of Belgian-made ammunition was found to be undercharged. The internal pressures were 15% lower than they should have been. This batch had reached several test sites before anyone noticed. The engineers at Herstal expected total failure, assuming the devices tuned for standard pressure would fail to cycle correctly. However, reports from Norway showed the FAL prototypes were still running. The testers had noticed the weaker performance and simply turned up the gas regulators to compensate for the lower powder charge. The units cycled perfectly with the bad ammunition. When the correct supplies arrived later, they just turned the regulators back down. There were no mechanical breakdowns and no parts needed replacing. The hardware had absorbed the inconsistency without a hitch. This moment proved what Saive had known from the start. Reliability isn't about stopping variation, it's about tolerating it. The quality of supplies, the level of maintenance, the environment, and the user's training will always vary. A tool that requires all those factors to be perfect will fail the moment one slips. A tool that can adjust will keep working when perfection is impossible. NATO evaluators didn't immediately buy into this. They viewed the regulator as an extra training burden for the user. Saive argued the opposite. It actually made training easier. A user didn't need to be a mechanic to fix a malfunction. The logic was simple. If the casing won't clear, add more gas. If the kick feels too strong, turn it down. The mechanical reasoning was easy to see. By mid-1954, the political winds shifted. The US moved forward with the M14 to protect its domestic industry. Britain followed the NATO standard and moved away from the EM2. This left smaller European nations with a choice: use American designs and become dependent on them, or license the FAL and keep their own manufacturing. Belgium, Canada, Australia, and eventually over 90 other nations chose the FAL. They didn't pick it for one single stat, but for the control it provided. The gas regulator was the symbol of that control, a mechanical admission that local conditions matter more than a one-size-fits-all rule. Saive never claimed his design was the greatest of all time. He claimed it was the most honest. It didn't act like ideal conditions were real. It didn't expect perfection from the user or the logistics chain. It worked with what was on hand. In doing so, it changed the definition of reliability. It wasn't about perfect performance in a lab, but about acceptable performance in the real world. The gas regulator, a simple rotating part, was the heart of that idea. It turned a rigid system into an adaptive one. It allowed for reconfiguration without taking it apart, adjustments without a toolbox, and tuning without an engineering degree. It wasn't the most complex part of the design, but it was the one that explained the entire project. By the time production ceased in the 1980s, over 2 million FN FAL units had been built. They were used by over 90 nations on 6 continents. The design was licensed to the UK, where it was known as the L1A1, and manufactured in Canada, Australia, Brazil, South Africa, and Israel. Each country made it their own. Shorter barrels for airborne units, tougher frames for harsh climates or different sites. Yet the gas regulator stayed the same. It was the one constant in a design built for change. The legacy of the FAL lasted far beyond its time in active service. It proved that reliability could be built through mechanical tolerance rather than just tight precision. Future systems, especially those meant for global use, began to include similar levels of adjustability. The concept that a tool should work across different philosophies, not just within one, became the new gold standard. Designers stopped asking, "What is the perfect setup?" and started asking, "What range of setups must this handle?" Saive didn't live to see the FAL leave most inventories. He passed away in 1970 while the design was still the standard on 4 continents. But back in that Herstal workshop in 1953, he understood a truth that would take the rest of the world decades to put into words. The most successful systems aren't the ones that are perfect in a perfect world, but the ones that are good enough in a messy one. The gas regulator was never the star of military history books. It didn't win a specific engagement or change the face of strategy. But it allowed the FAL to operate in places where more advanced designs simply quit, because high sophistication often relies on conditions that reality doesn't provide. The regulator was a nod to imperfection, and there was a certain wisdom in that. It accepted that users wouldn't always have the best supplies, that maintenance would be skipped, and that the weather would be unpredictable. It built forgiveness directly into the machine. Looking back, the gas regulator signaled a major shift in engineering during the mid-20th century. Designers realized that systems meant for global use couldn't assume local consistency. This lesson eventually touched aircraft, vehicles, and even power grids. Adaptability became a requirement. The FAL was the physical proof of this shift before the terminology even existed. When Saive clicked that collar in 1953, he wasn't just adding a feature. He was setting a principle. The world is unpredictable, and systems that ignore that fact will fail when the stakes are highest. The FN FAL was successful because it was honest about what was needed to handle imperfection. That honesty, contained in a simple rotating mechanism, allowed it to outlast almost all of its rivals. The gas regulator wasn't just a fix for one problem. It was the answer to the question Saive spent his life answering: how do you build something for a world you cannot predict? If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.